So, all right, welcome back. And this is our part 5 on Python for engineers. And here we are going to talk about NumPy. So, as engineers, you are highly likely that you would be doing numerical computation using Python, right? So, and if you are doing numerical computation using Python, then it's highly likely that you are going to use NumPy. NumPy actually provides you very fast and reliable array computations. And we're going to see why using NumPy arrays is actually preferred over using standard Python lists, right? And NumPy also provides certain interfaces to other packages, and almost all scientific Python packages that do scientific and engineering computation like that, do depend on NumPy. So NumPy is one of the fundamental building blocks of this Python scientific ecosystem. So if you're doing any scientific or engineering computation using Python, then it's almost a certainty that you are going to use you are going to use NumPy. So NumPy is one of the fundamental libraries. It was developed by Travis Oliphant, who was a signal processing engineer, who was actually doing his PhD in signal processing. So basically an electrical engineer. And during that time, he actually created this NumPy library for his own work for doing signal processing. And this actually has now become way beyond what Travis Oliphant originally intended. So NumPy is often used in addition to two other more popular packages, or rather two other popular packages, namely Matplotlib and SciPy. Matplotlib is used for plotting and SciPy is used for scientific computation. So actually NumPy provides the basic building block of doing scientific computation. So NumPy provides fast array computation, okay, mostly that, and built upon that you have Matplotlib and SciPy. SciPy gives you many modules for doing scientific computing, right? And Matplotlib gives you a fantastic library for doing plotting, okay? And on top of that, you have thousands of libraries that actually build upon these foundations. Someone is asking, is this like math function in Java and C? So yes and no. NumPy is like the math function in Java and C, but this is like, you can imagine the math function built in the math library built in Java and C. Those things are pretty much like the built-in math library that is available in Python. Okay, so the built-in math library that is available in Python. Okay, you can imagine the built-in math library of Java and C to be similar to that. But this NumPy library is way beyond that. So this is, I mean, something much bigger than this, right? And for that matter, SciPy actually provides hundreds of functions, if not thousands of functions, achieving different purpose in mathematics. So if you are studying statistics, you would find usable functions in SciPy. If you are doing signal processing, you're going to find usable functions in SciPy. If you are doing any part of electrical engineering, you're going to find out usable functions in SciPy, right? If you're solving differential equations, maybe you're going to find functions for those in SciPy. So right, so if you're doing quantum mechanics, you're going to find functions for that as well. So you can understand what I'm saying, right? If you're doing image processing, you would find suitable functions in SciPy. And of course, you have specialized library that actually build upon those foundations led by NumPy and SciPy. SciPy stands for scientific computing, and scientific Python, and NumPy stands for numeric Python, right? All right. So today's presentation is going to be today's class is going to be slightly different from our usual classes. In our usual classes, what I usually do, I usually type in code, and that usually takes a long time. Okay. And today, if I do today's class like that, it would be not less than 2.5 hours, right? And I wouldn't want you to wait for 2.5 hours, although you have done it in the past. But today I have prepared a presentation, and we're going to kind of go at a faster speed in this particular one, because otherwise we won't be able to end this in a standard amount of time. Right? So we have a lot to do. So let's start our discussion. So this Python's Jupyter Notebook actually provides a way of doing this kind of fantastic presentation out of the Jupyter Notebook. So this is like a PowerPoint slide that I'm going to show you, but except that this is made in Python. So that way what happens is every code that you see on this set of slides are executable. So I will be able to modify the code that I have written here and execute them on the screen like that. But although the format is like a presentation, right? So today we're going to talk about NumPy, so numeric Python, the fundamental building block of all scientific computing package, right? Yes, I am currently doing it on my own computer. I'm not running it on Google Colab, right? But for the most part, if you want to run the code, you can always run this on Google Colab. But again, I will provide you the Jupyter Notebook file after this. And if you are running it on Google Colab, all you have to do is to open Google Colab and then go to import, and you can import the Jupyter Notebook file, this file here. Okay, you can import this file. So just like you can make a Word document and import that on Google Docs, you can do the same thing like that, right? This file will be provided to you. With that said, let's proceed. Right. So again, don't worry about reading any of this stuff, but the main point that you have to understand is that Python list, I told you earlier, Python list and Python dictionary, those data types are way too generic for being fast, to be fast rather. Okay, so those data types like Python list and Python dictionary are too generic to be fast. So that way, if you are trying to do some real-time computation, or if you want your computation to be fast, then it is kind of advised against using those kind of libraries, against using NumPy, Python lists and Python dictionaries for storing your data, right? So what if you want to do some linear algebra, right? Maybe you want to do some computation on an array. But if you create that array as a list, Python list, then accessing the list will be much slower compared to a NumPy array. NumPy array is homogeneous in nature. Python lists are not homogeneous in nature, are heterogeneous in nature. What I mean by that is a single Python list can store many different kinds of data all at the same time, right? You know that. But a NumPy array won't be able to do that. So if you are storing floats on a NumPy array, you can only store floats. If you are storing ints, then you can only store ints, right? Just like that. So if you are storing complex numbers, then you can only store complex numbers. The point is the NumPy array is heterogeneous, and under the hood you have Fortran and C libraries, so that are actually working under the hood. So what happens is when you declare a NumPy array instead of creating a Python list or something like that, so what that is actually translated to a native C or Fortran array instead. Okay, and those programs are written by very experienced professionals in the domain. So even if you handcraft your code in C, you are quite unlikely that you would match their performance, because the code that is written here, that the C programs and the Fortran programs that are used under the hood are written by experts with many decades of experience, right? So you get the point. So this allows you, so NumPy acts as a wrapper. What is the wrapper? Wrapper gives you a high level interface of accessing low level information, right? So this program, NumPy especially, acts as a wrapper. So what happens is under the hood you have compiled C and Fortran programs. But instead of just calling the C and Fortran programs from C or Fortran, you're actually calling them from Python. So that allows you to write simpler code. So this does not take away the simplicity of Python, right? Python is so famous today simply because of its simplicity, for how simple it is. So NumPy does not take away from the simplicity of Python, but with that, without taking away the simplicity of Python, in addition to that, it provides you the speed that comes with C compiled languages like C and Fortran. Although Python is kind of half compiled and half interpreted, but that's not an issue here. That's not the point here, right? So NumPy actually provides you high performance arrays and vectors. That's the point you have to understand, right? So in order to use, so is this visible? I think it's visible, right? So please tell me if the code that appears here is not visible properly. Alright. So how do you import NumPy? Very simple. You say import NumPy as an alias. So I'm importing NumPy as NP. And forget about the next line. This is my personal preference. The next line is my personal preference. So here with this line, what I do is that by default, NumPy would represent all the floating point numbers. I mean, so if there are like 10 places after the decimal point, it will write down everything. I don't like that. Okay. Alongside that, it will actually show you 10 to the power, things like that. So I don't like that. So what I'm doing right now is I will be only printing up to 3 decimal place here. So that is what I have said here. You shouldn't do that. But and again, so just forget about this line for the moment. Okay. So the way you are going to import NumPy is import NumPy as NP. Okay. That's one of the standard imports. That is how you actually do it, right? So whenever you say NP dot, okay, so NP dot and write something, then you'll be calling a module or a function or something from inside NumPy. So let's run that. So I have just run that. Okay. So how can you create NumPy array? You can create NumPy arrays in many different ways. You can convert a compatible Python object, namely like a list, to a NumPy array. You can use something called you can use NumPy built-in functions like for creating arrays natively, or you can read CSV files or certain data files as NumPy arrays. So we're going to look into the first two options here. Okay, we are going to convert Python lists and objects like that into NumPy arrays, and then we are going to see how we actually can use native built-in NumPy functions to actually create arrays. Okay. So now when I say array, don't think that we are going to talk about just basic arrays. We are also going to talk about mathematics in general. Okay. And we shall also treat arrays as matrices as well. Right? So we're going to talk about linear algebra as well. Okay. But this talk on NumPy is never complete without talks on Matplotlib and SciPy. So we shall have discussions on those, Matplotlib and SciPy, and a complete discussion on NumPy, SciPy and Matplotlib makes makes it whole. Otherwise, simply discussing NumPy is not a complete discussion per se. Alright. So how can you create a NumPy array? Again, if you cannot see what is there on the screen, just make sure to let me know. So how do you create a NumPy array? It's very simple. From the NumPy module, all you need to call is the array function. So from the NumPy module, you call the array function and you are passing in a Python list. So this is a Python list. So you are going to pass in a Python list, okay, into the NumPy array functions. So you're going to call np.array and you're going to pass in a Python list, okay, and that will create a NumPy array from the Python list. Only one point to note here though is that the elements should be homogeneous. Here on the list, even though Python list is itself heterogeneous, but if you are trying to convert the Python list into a NumPy array, so the data that you are containing within the list should be only of the same data type. So here I have only integers, right? So now what we have is a NumPy array, and let's, instead of saying print v, I'm just typing v. So now the object is of array type. So v is a NumPy array. So you can just convert a Python list, okay, and convert a Python list like that. So instead I could do this, my list. Instead I could say that this is my list. I could have this list before I even do this. So I could have created a list and called it my list, and then could have passed it into the NumPy array function. Okay, so by doing that, what I would have done, actually the same thing. I would have converted this my list into a NumPy array and assigned it to the variable v, right? Just like that, done, right? So as you can see, this is a presentation format, but I can modify, write, execute code as I wish, right? All right. You can also provide multi-dimensional lists like that. So so this is kind of a list. Again, look very carefully. This is a list. This whole thing is a list, and the list itself contains list like that. So now, and this actually gets converted to a two-dimensional array. So now I have a two-dimensional array. See? So now this is a two-dimensional array. Okay? And of course, for any any multi-dimensional array, the dimensions should match. So if I have two elements on the first row, then on the second row also I need to have two elements. I could have three rows like that. So for example, some other elements. Now I have three rows, but each row would have two columns. If I somehow manage to delete one of the elements from one of the rows, so then the first row contains two elements, the second row contains two elements, but the third row now contains one element only. This will result into an error. So rather, not an error, but it won't be able to convert it. So let me just again, instead of printing, let me just say, so this is kind of now not a NumPy array anymore. Okay, this actually is made a NumPy array of Python lists. So this is not what I wanted. So if I do this, what happens? Now I have a NumPy array, proper NumPy array, right? So of course, very simple like that, right? So I think you understand what I'm saying here. Got it? So let's go to the next one. All right. So of course, you can always check the data type of any object in Python, and by simply using the type function. And if you see the data type of v, which we created earlier, the very first array we created, so the data type of the objects are NumPy N-dimensional array. ND array stands for N-dimensional array. So NumPy by default provides you a way of creating N-dimensional array, right? So a one-dimensional array would be just a straight array, right? So like a vector, right? A two-dimensional array is like a matrix. A three-dimensional array is like a matrix, and then another matrix right behind it, another matrix right behind it. An example of that would be like a color image, for example. A four-dimensional array would have another dimension to it, something like a video. Okay, so a video is essentially a four-dimensional array for that matter, right? So NumPy provides you very fast, really very fast and optimized N-dimensional array objects. So the NumPy arrays that you create are NumPy ND array objects, right? But they are kind of interoperable with Python lists, and Python lists are also interoperable with NumPy arrays for the most part. All right. All right. Now, of course, the moment we are creating array or matrices, then they would have certain shape, so dimensions, right? So you say that I have a 2x3 matrix like that. So I have 2 rows and 3 columns like that. Okay. V was a one-dimensional array, so it only had 4 elements. And M was a two-dimensional array where I had 3 rows and 2 columns, right? So I can figure out the dimensions by using the name of the variable where I stored the data. Okay. And with a dot notation, I can, so this is not a method call. Okay, this is an attribute of that particular variable. This is an attribute of that particular variable. So if I say m dot shape, then so NumPy array dot shape, then that gives me the shape of that particular object. So if it's an array, then it shows me the dimensionality of the array, right? So the number of rows, number of columns, number of depth rows, or whatever, like that, right? I can also calculate the total number of elements. So M was a two-dimensional array, if you recall, and two-dimensional array, it had 3 rows and 2 columns, so it had a total number of 6 elements. I can see that by using the size attribute. So if I say m dot size, it shows me the total number of elements in the array, like that, right? So, but also NumPy has built-in functions for calculating the shape. So from NumPy I can call the shape function that actually returns the shape of the array, and also NumPy has built-in size function. So from that I can actually calculate the size of the array. So it's the same thing, okay? So of course, if you're doing numerical computation, you might want to look at the size and shape of the matrices that you're actually getting, right? Okay, so far these are the advantages. So far what we have seen is like NumPy array as, what should I say, as homogeneous Python lists, right? But in addition, okay, NumPy arrays are statically typed. So NumPy arrays, so elements in NumPy array, they have static data types. Okay, so what I mean by that is they are going to be predefined, right? So if you are creating an integer array, it is going to hold integer values. If you are creating a float array, wow, hold on. So if you're creating a float array, okay, array containing NumPy array containing floating point numbers, then it's only going to store floating point numbers, right? So that way it's like a C and Fortran array, right? Okay, so if you're creating an integer array in C, it is only going to store integers, right? It is just like that. Okay, and NumPy arrays are homogeneous. This is the point to note here. NumPy arrays are homogeneous in nature, so basically you cannot have mix and match data types like that. So why is it so? The main point is that NumPy arrays are memory efficient and they are really fast. Okay, the implementations are so fast that it can often, supersede the speed of native C and Fortran implementations. Okay, because these are implemented by very optimized C and Fortran programs under the hood. Okay, so just keep that in mind. So that's the whole purpose, right? And just as an example, a NumPy array, using NumPy array instead of Python lists, if you're doing numerical computations only, can give you about from a minimum of 10 times speed boost to 100 times speed boost. Okay, your code would probably run 100 times faster if you are actually using NumPy arrays instead of native lists. Alright, so using the D type attribute, I can see what data type it has. So M, I created M as an integer array, so it is now storing 64-bit integers. Each element is a 64-bit integer. I can now, if I, so M, so just so that I know, so that I show you. So M was this array, right? So this was the M, right? M array, right? So I created moments ago. And if I say the data type, what is the data type? 64-bit integer. So each element in that array contains a 64-bit integer, right? So integers with 64-bit data, right? So in C programming language, it will be long integer, long int, or just long, right? Now, if I want to assign a different data type like that, so for example, at the 00 index, okay, if I want to assign a string, it will result into an error. It will result into an error saying that you cannot assign a string to an integer. That is what the point is here, that NumPy arrays are homogeneous in nature. They can only store the same type of data, right? So if you are storing integers, then you can only store integers in that array. If you are storing floats, then you can only store floats in that array, like that, right? So you cannot just randomly assign a new type of data to that. Okay. Okay. Now Now you can force to change the data type. You can force NumPy to change the data type. So when you create a NumPy array, you can declare the data type. So even if you are writing, let me show you. Even if you are writing integers by default, say by default, what happens is these numbers are treated as integers, right? So these numbers are treated as integers. So let me just print the type of m as well. So sorry, type of m dot d type. Okay, so of course m is an integer array, okay, because every element here is 64-bit integer. But what if I want to store the array, create an array with float, for example? So what I would do, I would say d type equal to float. Now these numbers will be converted from integer to float. Okay, so if I run this, as you can see, there is a dot right after every one of these numbers. So it indicates that it has been converted to a floating point array, right? Not just that, so that was an integer array, right? So if one of the elements is a float, for example, if this is, instead of being 1, if this is 1.0, so 1.0 is not integer 1, 1.0 is floating point 1, then the array will also become a float, without me explicitly saying that I want a floating point array, right? But if I take away the 0.0, then it becomes an integer array. It once again becomes an integer array, right? So I can force the data type, or if one of the data type, so for example, if one of the numbers is a complex number, so I have given this as an integer, this as an integer, but this is a complex number, this is again an integer. Then what happens is the entire array is created as a complex array. So all the elements will be complex elements, right? So you can understand integers are subsets of real numbers. So integers are subsets of floats, and real numbers are subsets of complex numbers. So complex number is a bigger data type in that sense. So everything will be converted to complex numbers, as you can see. So 128-bit complex number. So the 1 has been converted to 1 plus 0j, then 2 has been converted to 2 plus 0j, and just like that. So it has been now converted to a complex array, right? So even if I don't have a complex array, so what if I want to force it to become a complex array? I can say d type equal to complex, and that way I would have converted everything to a complex array. I have so this is kind of a forced conversion, right? And if one of them is of a particular data type which requires a bigger data type, then everything will be uplifted to the bigger data type here. But again, the point to note here is that everything is homogeneous. Okay, if one of them requires complex, everything becomes complex. If one of them requires float, okay, then everything becomes float. Okay, so whatever is the highest data type required, everything becomes of that data type. Okay, there is, before you ask, there is also it also works the other way around. If you say 2.5, just a moment, just to show you, if you say 2.5, then of course it's a floating point array, right? So the first one is 1.0, the second one is 2.5, it's created as a floating point array. But what if I write 2.5 here and force the data type to be integers? I could do that as well. So I could say d type as int. So I have now written a floating point number here, but I have forced the data type to become an integer, right? So I have forced the data type to become an integer. So what happens? Of course, 2.5 has been now truncated to 2. 2.5 has now been truncated to 2, right? So by default, if I did not force the data type, this would have been a floating point array, right? All the elements would be floating point numbers. But if I did force the array to become something else, to become a lower data type like an integer, its requirement was a float, but I converted it to an integer, then everything will become integers. You get the point, right? So if I want to convert it to a complex array, I can do it. So that's the point. Data type is taken as the highest data type that is required, by the array, or if you force a data type, then it will be converted to that forced data type that you are creating. And also if you are having complex numbers here, and if you say int or something like that, then only the real part will be taken. All right. All right. So now NumPy provides you something like array generating functions, right? And let me give you a few examples of array generating functions. This is like the range function in pure Python, but from NumPy, if you call a range, okay, a range stands for array range. So you are creating an array. Yes, I will definitely. Someone is asking, am I going to share these notes? Definitely, I'm going to share these notes. Just as I usually do. This file will be shared as a Google Colab file for you. Okay, this will appear as a regular Google Colab file for you. Okay, for me, it is appearing as a slideshow, but for you, it will be appearing as a Google Colab file. So don't worry about that. All right. So if I create a NumPy array, so I can create a NumPy array through the arrange function, right? Just see. So it's an array range. So now this is the starting point of the array, and just keep in mind that these are one of the most used functions, and we are going to use those functions for doing control system analysis, later on signal processing as well. Okay, so the function starts from, so basically we are creating an array that starts from 0, ends at 10 but not including 10, with an increment of 1. So right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be the array. So if I print it, so that's the array. But now just notice that this X here is a NumPy array. Okay, it's not a Python list, it's a NumPy array. That's the difference here. Okay, so I can do very similar things. I can start at, say for example, -1, end at 1. Again, I am starting at -1, ending at 1, and with a step of 0.1. So the array I am going to create is going to be something like -1, -0.9, -0.8, and it will go on increasing up to 0.9. It cannot touch the right hand limit, right? Just as per the standard Python convention. So as you can see, we have created a NumPy array starting from -1 and incrementing from that with a step of 0.1, just like that, right? I could have created an array like this. So for example, starting from -2.5 maybe. Okay, so you can see. Just before you ask, I could have gone the other way around. Maybe I'm starting from 2.5 and I want to go down to 1, but not touching 1, in the step of -0.1. So it's a decreasing array. That is also valid. It is a decreasing array. Of course, starts from 2.5 and then goes on decreasing up to 1, but not including 1. Okay, in the step of -0.1. So basically decreases in the step of 0.1, like that, right? So these are the things that I could do. All right, so let's go to the next one. Okay, where have I gone to? All right. All right. Along with that, along with arrange, there is a linear space function, and you have actually seen the arrange function before. So here is the linear space function. So linear space functions are very similar, but only point to note here is that instead of defining the step size, okay, we are defining how many points I want. So I am saying I want 25 points. How many points do I want? I want 25 points. I want to start at 0 and end at 10. But both the lower limit and the upper limit are included. So I am going starting from 0 and ending at 10, including 10, right? I'm not excluding 10, not going up to 10. So it's like up to and including 10. So both limits are included here. And here, so in the arrange function, if you go back in the arrange function, this element gave you the step size, okay, the gap between the successive elements, okay. And in the linspace function, this element actually gives you the number of elements you want, okay, number of elements you want. So depending on your use case, you are either going to use arrange or you are going to use linspace. So it's starting from 0 and ending at 10 as expected. Okay, and it is creating 25 points in the array. So it is creating an array that starts at 0, ends at 10. Okay, and there are 25 points in between, right? Now question is, why would I need such arrays? I would need such arrays simply because I might want to do certain computation over an array. So I might want to calculate the value of sign, or maybe a value of a function over a certain values of frequency or certain value of time, something like that. So for example, if I want to compute the output of a system for every single second from time t equal to 0 up to time t equal to 10, right? So I would create an array accordingly, and then at every second I am going to compute certain things, right? So for that I would need an array that holds the number, holds the time, right? And then I shall use the array to compute some things, maybe the response of the system and things like that, right? So things like that. Okay, then just like linear space, you also have logarithmic space, or rather log space, and I'm not going to explain this at this moment, but we did use this in our frequency response analysis classes, but I'm going to not explain this here. Okay, we are going to learn how to do Bode plots and everything in using Python later on, and there we are going to actually I'm going to talk about how this thing actually works. Okay, also there is something here I'm not going to so these are just there for the sake of completeness. Here you can create arrays that look like this. I mean, why would you need arrays that look like this? Okay, as you can see, like arrays like 0 0 0 0 1 1 1 1 2 2 2 2 3 3 3 3 4 4 4 4, something like that. Those arrays are useful for doing 3D plots. Okay, and we're going to see that later on. Okay, so again, plotting that, you can also create arrays like that. Okay, all right, now let's talk about random data. We often need random data for doing different analysis here. One of the most popular use of random data or random values, random numbers, is encryption, right? Right now, whatever data that you are transmitting or receiving over the internet are encrypted, right? Password protected, right? So whenever you do password protection, how does that work? Your computer actually essentially generates a very big number which is not easily factorizable, and based on the factors of that number, so again, I'm not going to tell you how these things work, but the point is your computer kind of depends on generation of random numbers, okay, to encrypt, okay, to basically password protect your information, right? So whenever you are doing something on the internet, on your web browser, you see a small lock symbol, right? And that says HTTPS, okay? So you are doing secure communication, so it's basically encrypted, okay? And that encryption kind of depends, or rather for the most part depends on random numbers. Okay, so random numbers are very useful, really important for our everyday life. Okay, and Python provides random numbers by default, and there are several kinds of random numbers. So random numbers are actually often taken from different distributions. Okay, by default random numbers are taken from uniform distributions. So you would have a uniform distribution between 0 and 1, and you're going to randomly pick a number from that. You can have a normal distribution between with a certain mean and certain standard deviation, and you can pick numbers from that as well. Okay, here is an example of a 5 by 5 random array. Now if you run the function in your computer, this is not going to turn out to be the same, right? Because random, right? So again, every single number that are presented here, so the result is a 5 by 5 array, right? Array that contains 5 rows and 5 columns, but each element is drawn from a distribution, uniform distribution between 0 and 1. Okay, so every element here has got an equal probability of being drawn from the uniform distribution, right? So it's just like that. So I could have created a different sized array. So I could have created an array that had 5 rows, but say for example 7 columns. So now I have created an array of 5 rows and 7 columns, like that. Okay, so it's a random array. So every element is a random number drawn from a uniform distribution between 0 and 1. All right. Okay, so that was drawn from a uniform distribution, right? And what if I want to draw numbers from normal distribution? Okay, standard normal distribution. What is a standard normal distribution? It's a normal distribution with 0 mean and variance of 1, right? So again, I'm not going to go to the statistics here, discuss the statistics here, but here. So set of random numbers drawn from a uniform normal distribution. Yes, someone is asking, can we change the range? Absolutely, I can change the range, and I'm going to talk about that. Okay. Okay, I did not talk about that. So let's do that. Let's do that. Okay. Let's change the range. For example, let's say, let's here, go back. Let's go back. Okay, fine. So I had a random number like that. So what if I just call this? What do I have? I have just a single random number, right? So if I run it once more, I have another random number. If I run it once more, I have another random number. So I have a random number between 0 and 1, right? I have a random number between 0 and 1. What if I want a random number between 0 and 10? What if I want that? What would I do? I would just multiply this with 10, right? So that way, every time I run this, I get a random number between 0 and 10. Because the original random number was between 0 and 1, I am multiplying that with 10. So the random number that I now get will be from 0 and 10, will be between 0 and 10, right? What if I want a random number between 0 and 20? Just multiply it with 20. So I get a random number between 0 and 20, right? Then every time I run this, it will be a different number altogether. What if I want a random number between 5 and 15? Say 5 and 15. So the minimum value should be 5, right? Minimum value should be 5. So 5 and, try to understand. What if I want a random number between 5 and 15? Let's go back to understand this. So if I say this, so this itself generates a random number between 0 and 1. Multiplying that with 10 will give you a random number between 0 and 10, right? So the minimum possible random number would be 0 and the maximum possible random number here would be 10. What if I add 5 with this? Then what happens is this 5 is a deterministic value, right? Then what happens is the minimum number that I generate out of this is going to be 5. Because this is going to give me a number between 0 and 10. I'm adding 5 with this. So now I have a random number between 5 and 15, right? Right? So every time I run this, I would have a random number between 5 and 15, right? See. And not only that, I could have created an array. I could have created something like a 5 by 7 array that contains random numbers between 5 and 15. So now, see what I have done. I have created a 5 by 7 array. Okay, so array that has 5 rows and 7 columns, right? And each element is a random number drawn from a uniform distribution that starts at 5, ends at 15. So every element of this array is a random number between 5 and 15, right? What if you want an integer? Okay, what if you want an integer? What would you do then? Okay, then this is the NumPy array, right? Let's call the array function again on top of this. Okay, again call the array function, and now I can declare the d type, and I can say d type equal to int. So every number will now be converted to an integer. Let's run that. So what happened? Hold on a second. Okay, that got messed up. Just a moment. Okay. What happened? I was supposed to convert the whole thing into an integer. Just a moment. Okay. So what if I want? So again, let's go back. So these are random numbers between 5 and 15. I can convert the whole thing into an integer. So I can say np dot an array. So the whole thing is a NumPy array, and I can say d type equal to int, right? Now look carefully. I have random integers, okay, between 5 and 15. See, running this once more. random integers between 5 and 15. Once again, random integers between 5 and 15. So it's an array of random integers, okay, and the dimension of the array is 5 by 7. Just one point to note here, the upper limit, okay, someone is saying, let's change the range once more. Let's say I want an array. So can you tell me a range? Can you tell me a range? Just for your purpose, can you tell me a range? There is a slight delay between what I say here and when it reaches you people over the YouTube. Someone is saying 1 to 17. So the minimum value has to be 1 and the range would be 16 that way, right? So this way, this generates a random number between 0 and 1. Then multiplying that will create, see, that with 16 would create a random number between 0 and 16. Then I'm adding a 1, so I would have a random number between 1 and 16. So random integers here, okay, between 1 and 16. See? I'll get that point, right? So let's read everything here. You just have to keep this in mind. Rather, instead of deleting it, let's keep that in comments, right? Because in the future, you might want to look at this one. Anyway, so we have just gone back to the original slide. All right. So I believe I have discussed this, the normal distribution. All right. Right. So we have seen how we actually create arrays with the array function. We have seen how we actually create arrays with the. Hold on for a second. That's diag. That's fine. Diag. And what should I say? Okay, I'm going to see whether these are there. Hold on. Okay, right. So now we can create an, again, these are, I mean, often required in many cases, right? I want to create a diagonal matrix, right? What if I want to create a diagonal matrix? What is the diagonal matrix? I only have elements in the diagonal, principal diagonal, and everything else is a 0, right? So something like that. Say, for example, right? So I have a 5 by 5 diagonal matrix, okay? So only the elements in the principal diagonal are there, right? So I can also offset the principal diagonal by a certain value, right? So now the principal diagonal, instead of 1, 2, 3 being on the principal diagonal, they're on principal diagonal offset along that by one element. So now here I have 1, 2, 3 like that. So I could say 1, 2, 3 minus 4, 10. So that will now create a 6 by 6 array where this here, this is not the principal diagonal, right? This here has these elements 1, 2, 3, 4, minus 4, 10, whatever. So you can create these arrays. This kind of arrays might be required for some kind of computations, okay, depending on what you're doing. All right. Again, these are just syntactical things that you have to understand. So this is actually kind of a sort of a showcase of how powerful this library is. I mean, being able to do these things, I mean, if you have to write these modules in native C or something like that, you would be in a lot of trouble. Like, you have to think about a lot of low level details, but Python spares you that trouble, right? All right. Oh yeah, I was talking about this. You can create arrays that only holds zeros, right? We often create placeholder arrays, right? Often what happens is I want to have a blank slate like that, right? I want to create an array that only contains 0 so that I can later on add some numbers there, right? So NumPy has a function called zeros. If I say np.zeros, okay, and pass in the dimension of that, okay, then I would be able to create an array containing zeros, okay, with that dimension. So I would have now a 3 by 3 array that only contains zeros. I could easily have a 3 by 10 array Who knows? So 3 rows, 10 columns containing only zeros, right? The same thing happens with np.once. Same thing happens with np.once. I can pass in the dimension here, and subsequently it will create an array that contains 1 1 1 1 1 1 1, right? Just like that. And just as usual, I could change the dimension. I could have said, I could have easily said that fine, let's make this 7. Alright, so I have a 3 by 7 array, maybe 4 by 7 array, who knows? A 4 by 7 array that only has 1. Very simple. What if I want an array that only has something like 25? So I would multiply this with 25. So it's an array where all the elements are 25. Got it? So these functions are pretty handy, and this kind of allows you to not write a for loop. In Python, it is always recommended that you don't write a loop unless it is really necessary. Unless you cannot get away without writing a loop, you are not supposed to write a loop in Python. Okay, you are supposed to avoid loops as far as practicable, right? And there are reasons for that. Python looping, okay, is kind of slow by default, right? That is why you have something called vectorized calculations, right? You can pass in an entire array to a function, and the function will return an entire array to you. So for example, if you want to calculate the value of cosine, or maybe tan, maybe sine, over, say for example, over many different values, what you could do, you could run a for loop and calculate everything like that, okay? But you could also create a NumPy array and pass in the entire array to the function, and the function will return another array containing element-wise calculation of that. Okay. So essentially what happens is you can get rid of for loops very easily. So these are called vectorized computations, and vectorized computations are heavily optimized on your computer's processor. Okay, using vectorized instruction sets that are available on your computer. So using that, actually these would be way faster than your native C implementation even. All right. So now of course you understand indexing. Let me just write v. What v was a NumPy array. Okay, recall that. And if I just like a list, if I say v0, I get to have the 0th element out of this. Okay, if I say v2, I get to have the second element out of this. This is exactly similar to what I had earlier, right? Now let's talk about m, right? What was m? M was this array. Recall, m was this array, right? This was this complex array, right? Now again, m was this complex array. Now of course, just like that, so let me just print m. It prints like without the array thing. It's a two-dimensional array, right? Everything is complex numbers. So the first one is a complex number, the second element is also a complex number, like that. But as an array, as far as arrays go, this array, look very carefully, this array is a two-dimensional array, right? Alright? It's a two-dimensional array. And since it's a two-dimensional array, you know that there is another notation through which you can actually understand this, right? Since it's a two-dimensional array, you call each element with its row number and column number. So let me just to show this to you, let me just create let me just convert it back to integers, right? Let me say m equal to m dot astel. So this is another notation, right? You can actually, what is it? It gave me a warning. I don't care. Alright, so now I have an integer array. I just converted it back to integers. So it gave me a warning saying that if I convert a complex array to an integer array, the imaginary part will be discarded. I told you earlier. So I have discarded the imaginary part. Okay, just to show you properly. So here, this is the element at row number 0, column number 0, right? Look very carefully. This is an element at row number 0, column number 0, right? This is an element in row number 0, column number 1. Element in row number 1, column number 2. Sorry, column number 0. This is row 1, column 1, right? So now you can two-dimensional indexing. You can do two-dimensional indexing. So I can say 1, 1. So now I'm asking for the element at row 1, column 1. So this is row 1 and this one is column 1. So this 2 and this 4. These constitute the column 1. So element at row 1, column 1 would be this one. So see, that is 4, just like that. So that way you can extract any particular element out of an array, right? Just keep in mind that our indexing starts from 0, right? So if you have a matrix, you can extract any individual element using a 2D or multi-dimensional indexing like that. If you have a 3D array, you can do a 3D indexing like that, right? So again, just as simple, right? So M was this array, right? So again, now if I say M1, then it extracts the entire row 1. So this is row 1, right? So remember, this is row 0. This is row 1. So if I say M1, then it extracts the entire row 1. Now after that, if I say 1, so this indexing is very similar to the list indexing. Okay. So I'm extracting this, and after that, on that I'm doing another indexing, right? I'm doing another indexing, right? So that will extract this element, this 4, right? So if I run that, of course, just like that. So you can treat this as a list. I mean, the indexing will work as a list indexing, or also it will, I mean, NumPy arrays have better indexing features. Okay, but it is compatible with list indexing. All right. All right. So again, remember what M was. So I can use this kind of indices, two-dimensional indexing. So I can say, give me all the elements from row 1. Okay. So with this, let me actually show you better examples. Okay. Let me show you better examples. Let me instead create a random array. Okay. So okay, that's a random array. So np.random.rand and say I want it to be a 3x4 array, and let me print ran. Oh, sorry, print random array. All right, so I have this random array, right? So now on this array, of course, this is the element number 0, 0. This is element number 0, 1. This is element number 0, 2. This is at 0, 3, because this is at 0th row, 3rd column, right? Now I can say, give me all elements. So if I say this, what does this one mean? It means give me all the, so I'm looking for the element, or rather, let me just start with this. What does this one mean? I'm looking for the element which is at row number 1, column number 2. So which one is row number 1? So this is row number 1, and this is column 0, column 1, column 2. So this exact element will be extracted out of this. So this is the element. Now of course, here, since I did that print option at the very beginning, I told you I don't like those kind of messed up outputs. Here is what you see why, right? So if this number appeared in the array, it would have been hardly visible, right? So this was the element 0.43 whatever, right? So I've just extracted that out of this. Okay, that was the second element out of this. See, right? Now what is that colon symbol? You know, this colon actually indicates all, everything. So now if I say give me the element which is at row 1 but all the columns, so that actually tells you that I want all the columns. So yes, so it gives me all the columns of the first row. Similarly, I could say 2 here. That would give me all the columns of the second row. So this is the second row. Remember, this is the 0th row. this is the first row, this is the first row, and this is the second row. So I've extracted all the columns of the second row. I could have done the same thing. So this is like asking for all the elements in the 0th column. So I'm asking for all the elements in the 0th column. So if I do that, so all the elements in the 0th column. In the 0th column I have this element. In the 0th column I have this element, and this element. So I have that. Alright. So you can do this kind of indexings here. Alright. So that's not an issue, right? Alright. Of course, we are going to do slightly more complicated things than this. Alright. So instead of doing it on M, let's do it on RAN. Recall, what was the RAN array? This was the RAN array, right? So this was the array. I can assign any element with any value. Of course, these arrays are mutable objects. So I can say RAN and at index 0, 0. So this is the element I am talking about. At that index, I can assign some values, some other value. But keep in mind that this array is a floating point array, right? So I can only assign floating point numbers. So even if I assign an integer, that will be converted to a floating point number. And subsequently, say if I assign 1 and print RAN, then of course the first element becomes 1 point, so which indicates that it is still a floating point number. You get the point, right? So you get the idea. Alright? Right, let's proceed. So again, these ideas are pretty important for doing numerical computations, right? So whenever you're doing any numerical algorithm or implementing any numerical computation, doing any numerical computation, which as engineers we people do quite often, right? We actually need this kind of libraries, this kind of computational capabilities, right? Okay. So again, let me say, what was M, just to show you. This was M, right? This was M. Fine. Sorry, no, not M. Let's talk about the that array. So this was the array, right? Right, something like that. Now, what if I say take all the elements? So what are these? So this is like extracting all the elements of the first column, right? So all the elements of the first column. Sorry, not M, I'm talking about this RAN. All the elements of the first column. So this element, so this is the first column once again. This is the first 0th column, and this will constitute the first column. So I'm taking all the elements of the first column. So what are those? Yeah, these are those. And if I say 50, then all the elements of the first column will become 50. So if I print this, print after doing this, all the elements in the first column has become 50. See? So instead of printing, so just say that I have a comma after this. So now all the elements in the first column has become 50. So these elements have been changed, modified permanently. All right. And again, if you do these computations in your computer, the values would be different because all these numbers came from a random array, right? Of course, random numbers will be different every time, unless we seed it, which I am going to talk about later. All right. All right. Now there is something called index slicing in NumPy, and of course that is very similar to what we saw in our what should I say? In our Python list indexing, right? So again, let's forget about this. Let's print the RAN array. This was the RAN array, right? And now what if I rather let's create another array. Okay, fine, I am happy with this. Okay, what if I want to extract, you already know, if I say a1, then it sorry, not a, right? If I say ran1, so that gives me the first row. So this is the first row. Again, the top one is the 0th row. This is the first row. This gave me the first row, right? What if I say 1:3? What if I say that like that? So this will give me row number 1, row number 2, up to and excluding row number 3. You know that, right? So this is how you have to read it. So this is very much like Python list. So this gave me row number 1 and row number 2, up to and excluding row number 3, right? And if I say colon, of course it means all the elements, no changes. But what if I want to extract these elements, these two, sorry, what if I want to extract these two and these two, right? So these are so this is column number 1, so column number 0, then column number 1, then column number 2, and this is column number 3. So if I say something like this, what does it mean? It means give me the elements that are in row number 1 and row number 2, and in column number 2 and column number 3. So I'm extracting elements from row number 1 and 2, excluding row number 3, and I'm extracting elements from column number 2 and column number 3, excluding column number 4, of course, right? So if I do that, see, I have these elements, these two and these two extracted. So they belong to that particular location, right? So that way I can do those kind of fancy indexings that were actually there in our NumPy list, Python list, pure Python lists, right? So those will work here as well. Okay. Also, slices are mutable. Slices are mutable. What I mean by that is, again, let me show you the array. So this was the array. Now, at the very, say, I told you earlier that if I want to modify one single element, I can do that. So what if I want to modify this element? This is at row number 0, column number 1. So row number 0, column number 1. If I want to modify this with some other number, say maybe 2.5. So, and print the array after this. Of course, this has been modified to 2.5. So this column, in this column, this has been modified to 2.5. This was originally 50. All right, that's fine. But also slicing, after doing slices, I can modify the array. So let me show you. So if I say 0, and then say after that, if I say 1:3 or maybe 1:4, okay. So what am I extracting exactly? So from the 0th row, what is the 0th row? This is the 0th row. From the 0th row, I am extracting column number 1. So this is saying I am extracting column number 1, column number 2, and column number 3. So this is column number 1, column number 2, and column number 3. So these are the 3 elements that I am extracting out of this. So if I run this, these 3 elements will be extracted, right? So that's the slicing. What did I say? Yeah, these are the 3 elements that have been extracted, right? Those 3 elements. And now I can modify those 3 elements particularly. I could modify those 3 elements particularly, say, and of course, if I'm modifying 3 elements, I have to pass in 3 elements. And if I pass in 3 elements, say for example, if I say 2, 4, and 6, then this element is going to become 2, this element is going to become 4, and this element is going to become 6. So after this, if I print ran, what happens? This element has become 2, this element has become 4, this element has become 6. So index slices are also assignable like that. Alright. So this kind of array modifications are pretty much required if you are doing any kind of numerical computation. And as electrical engineers, you are very much likely to do numerical computations like that. Alright. So let's move forward. Right. So again, I'm going to skip this for a moment. Okay. Right. Okay. These are all the elements. Okay. These are all the elements in the using step size 2 and stuff like that. We're going to later on see how these things really work. I'm skipping a few slides here, but I have kept this for your for a complete discussion on everything. Okay. All right. Also you can of course count your array from the end. So this was your ran array, so that was the thing. Okay, of course after so many modifications. So if I say this one, so if I say -1, so that will be the last row. So if I say 1 is the first row, sorry, 1 is the first row, yeah. If I say 0 is the 0th row, right? So last row I am saying. Okay, but if I say -1, what about -1? -1 would be the last row. So if I'm counting from the last, counting from the end, then -1 indicates the end. So this is the last row. So what is the last row? This is the last row. All right, that's the last row. Okay, got it. Okay, and from the last row, maybe from the last row, if I want to extract the last two elements, from the last row, if I want to extract the last two elements, last row, last two columns. So from the last row, if I want to extract the last two columns, so here of course I will be going from -2 up to the end. So -2 up to the end. So this is something like the list indexing you saw, right? So I'm choosing the last row and I'm choosing the column that appears right before the last column. So this is that one. Okay, and then I'm going to the end. So that is how we write it. Okay, so not a, ran, right? So we have extracted these two elements just like that. All right, so you can do those kind of indexings back in here as well. So these indices are pretty much compatible with NumPy Python lists, right? Okay, again I am not going to talk about this. Let me keep it like this. And again, this is not going to run properly, so I'm going to probably skip this. Let me skip this. All right. Again, we have talked about this. Probably this is not going to run because this is going to, yeah, this is fine. This is fine. We're not going to talk about this. Right. Now look at this one. So extracting elements, modifying elements, this is one of the biggest parts of any linear algebra computation or any numerical computation, right? All right. So again, what was our array? This was our array, right? After all the modifications, right? So now if I say I have created a list, okay, I have created a particular list. So it says 1, 2, and 3. And what if I pass in the list to the array? If I pass in the list to the array, what happens is that row number 1, row number 2, and row number 3 will be extracted. All right, row number 3, row number 1, row number 2, row number 3 will be extracted. Unfortunately, I don't have row number 3, so it is going to show an error. Say I want to extract row number 1 and row number 0 and row number 2. What if I want to do that? Again, for your reference, that's the array, right? So what if I want to extract row number 0 and row number 2 particularly? Okay, so if I want to do that, I can run this. So now I have extracted row number 0 and row number 2 out of this. Okay, so we can do similar indexing like that. Okay, and so I can pass in the exact values of the rows and columns I want. So this is something, again, A wasn't defined because I just changed the name. So of course, column 2, column -1, okay, and this is not there, right? Column 1, column 2. Yeah, sure, why not? All right, so you don't have more than 2 elements like that. So the point being, you can specifically mention which rows and which columns you want to extract, and out of that you can do the extraction like that. So in any case, you won't probably need all these complicated computations, but it is good to know, for example, right? All right, again, these are certain things that I'm going to, all right, this is one of rather more important thing. I'm going to show you a few examples later on at the end. In any case, look at this one. For example, what I have here is again a simple array, right? And I have 0, 1, 2, 3, 4, right? Something like that. So instead of, who created this? All right, so fine, we have an array. So 0, 1, 2, 3, 4, right? Some elements like that. And now out of these, if I want to extract the first element, so 0th element, then not the first element, then this one. So if I want to selectively extract certain elements and let the other elements go, then I can create something like a fancy index like that. So I can create a list of indices that I want to extract and list of indices that I want to skip particularly, right? So if I want to do that, then I can create a mask like that. It's called a mask, and I'm going to talk about how these things actually are used properly. So I can do that. I can only extract those particular elements where these appears as true. So this is true corresponding to this, so I'm extracting this. This is false corresponding to this, so I'm not extracting this. This is again true corresponding to this, so I'm extracting that element as well. So this can also be done by doing the same thing, but writing 1 for a boolean true and 0 for a boolean false. I could do that. Okay. All right. So now this is kind of useful for checking conditional elements. Okay. For example, let's create a simple array, right? So again, arrange. Using arrange, I'm creating an array that starts from 0 and goes up to 10 in the step of 0.5. So I'm starting from 0 and going up to 9.5. Okay. So that's a simple array in the step of 0.5. All right. And now if I want to figure out this condition, okay, if I want to figure out this condition, so condition where x, so let me just show you this very simple thing. Okay, condition where x is less than 5. Okay, see what happens. So x is greater than 5, right? Look carefully. So this was the array, right? Now if I ask it, okay, fine. So let me show where x is greater than 5, right? So for example, let's go back. If, say for example, if x is a single number, say x is, for example, 10, and if I ask x is greater than, so it's a logical statement, right? You learned that in an earlier class. So it's a logical statement, and I'm asking whether or not x is greater than 5, right? And with that, it will return a true, right? Just a single true like that. But what if x is a NumPy array that has many elements like that? Okay, many elements like that. And now if I ask it, okay, tell me where x is greater than 5. Now it will return another NumPy array and telling me in particular where those elements are greater than 5 and where those elements are not greater than 5. So if the condition is false for a particular element, it will say false, and if the condition is true for a particular element, it will say true. Okay. This example will be better served with a slightly more complicated array. So say x is, instead of saying this, so So I'm creating an array of 20 elements, right? So again, random array of 20 elements where the numbers are drawn from 0 and 1. So some of the elements are going to be greater than 0.5, some of them are going to be less than 0.5. So this is greater than 0.5, this is less than 0.5, right? So if I say, if I say print x here, okay, and I'm going to print this as well, okay. So what I have is, look very carefully. So this was the original array that I just randomly created, okay. And now this next one particularly shows me which one of these, okay, what happened? Hold on a second. Did I run this? Yes, I did run this. Just a second. I ran this. Okay, I have to assign it to a variable, I think. All right, yeah, I have to assign it to a variable. Say mask equal to x greater than 5. So I have just assigned it to a variable. So what is the logical output of this? I have just assigned that to a variable. So not 5. What am I doing? All right, that's fine. X greater than 0.5. So what I have here, look very carefully. So I have that array. So this was the array, right? This is the array. And now I'm checking for the condition where x is greater than 0.5. So wherever x is greater than 0.5, it is showing me a true. And wherever x is less than 0.5, it is showing me a false. See, the first one, for this one, the result is true. For the next one, the result is false. For this one, the result is true. Sorry, false. For this one, the result is true. And as such and such. For this one, the result is false. Just like that. Okay. And if I want to extract only those elements for which the result is true, so what I can do, I can actually assign this to a mask, to basically a variable. I can say, call this a mask. So this mask will contain those positions particularly indicated by true where this condition was met, okay, and subsequently I can extract those elements for which this condition is satisfied. So if I run this, I am only extracting those elements for which the element is greater than 0.5. So this one was 0.5, so that has been extracted. Then this one was greater than 0.5, so this one is extracted. This one is greater than 0.5, so that one is extracted. Greater than 0.5, extracted. This one did not get extracted. This one did get extracted. Just like that. So with that condition, I can do this kind of modifications, and just like that. I can also do this kind of thing, do an AND operation and check for multiple conditions. Say if I want to also see whether the numbers are greater than 0.5 but also less than 0.7, right? So here I have this true, 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 and only a few trues, right? Where x is greater than 0.5 but less than 0.7. So right, so and if I extract those, I have this element, see, corresponding value is true here, corresponding mask value is true. So what I'm doing essentially, I have using a logical expression created a list, created an array that actually stores the locations from which I want to extract the elements from the array. So this is kind of useful to figure out when a signal crossed a certain value, okay, how long the signal was between certain values and such, right? For our purpose at least. All right. Alright, there are a few things that I'm going to skip in this. Okay, let's jump to linear algebra. So you people are familiar with linear algebra, right? Again, this is not a mathematics class in any stretch. So again, we are assuming kind of you know linear algebra, but again, we are going to talk about linear algebra in our theoretical classes. So whenever we actually need those things. But yeah. So again, let's create a very simple NumPy array. So what do I have is a very simple NumPy array. Again, starting from 0 going up to 5 in the increment of 1, right? I can do very simple array operations, right? I can multiply the array by a number. So if I do that, then what happens? Another array is returned with each element multiplied by that value. I can do addition. So from the original, with the original array, each element is incremented by a value of 2, like that. Okay. So every element operation is element wise, right? So if I so A is not defined, why not? So if I say v1 and v1, so if I say again multiplying by 2, like that. So again, it's the same thing, right? So let's create another array. Say another array. Say b dot. Okay. So this is again a random array, and so this is A. And if I want to multiply it with 2, say for example, of course you understand what happens, right? So each array, so this was the original array, and this is the array when I multiply the original array by 2, right? Just like that. So I can do all this kind of computations. So these are valid computations, right? Alright. So I can again square a matrix, calculate the square of a matrix. So I can do A star A. So basically so not a square, matrix square, but I can do element wise square of a matrix, like that. So that was the matrix, and we have done element wise square. So each element is squared up. I'm going to show you proper examples of this, right? So for this, say X is a very simple example. Say X is an array. So np dot a range from 0 to 10 and with a step of 0.1, rather step of 0.5 maybe, right? So X is an array that starts at 0, goes up to 10 with a step of 0.5. Okay, and let's print X, and then I'm creating another array Y, and Y now is something like X square. You know what X square is, right? So the symbol for square is double star, and print Y. Let's print Y. So now these are the values of X. So X is starting from 0, and in the step of 0.5 it is going up to 9.5, and here I have, see, so this has been multiplied, this has been multiplied, just like that. So this has been squared up, all individual elements have been squared up, just like that. Well, someone is asking how to make the random numbers appear as small. Okay, that is something I did at the very beginning. Okay, so just get along with this. I'm going to go back later on. Okay, so all you can do after importing the NumPy, if you want the random numbers to be printed in not, if you don't, rather, what should I say? If you want the numbers to be printed in a sensible manner, you can do np.set print options, and you can say pass in 3. So you want 3 decimal places, rather 3 significant digits. Okay, and you can say suppress equal to true. So whenever actually I am doing any computation with NumPy, after just importing NumPy, I do this personally. This is a personal preference. This does not do any changes in the internal computation that NumPy does. It only makes the printing prettier. Okay, I personally do this. Okay, np.set print options, and I pass in 3. So I want only 3 significant digits at most, rather, if possible. And then I suppress all those additional digits that appear. So that is something I do. Right. All right. So now this could have been done through a for loop, right? You could have done a for loop, and from the for loop you could have modified, taken each number from this and squared it up. But instead of running a for loop, you can very easily just take an array and square it up, right? And not just that, you can create, say, another array which is, say, np dot sign of x. Now what you have, and of course you have to print it, right? And what you have here is the sign of x. So basically sign x for each value of x in this array. So x is 0, for that sign 0 is 0. Then x is 0.5 radians, of course. For that sin x is this one. Then x is 1, for that sin x is this one. So the point being, you can, without using any for loop or any loops for that matter, you can do computations over an array, right? So if you have lots of number for which the same computation is going to take place, you can just do a vectorized operation like that. So NumPy functions do take this kind of vectorized operations, right? All right. So now with that said, let me just go for a bit. All right. So now let me create a new set of arrays. Let me say A is np.array. Let me create a 3x3 array. Okay, and is some suitable 3x3 array. Let me just think about it. 1, 2, and 5. Okay, 3 minus 2 0 almost, and say 7 2 minus 2. All right. So I've created a two-dimensional array, right? So let's say print A. Let's create another array. Let's say let's create another array. Say np.array, and now I'm creating a vertical array. So basically a vector. Say it's 20. It's minus 1. Sorry, not 20 like that. It's 20, and then it's minus 1, and then it's something. And what's something? Say eight. All right, say print B. So I have created two arrays. So this is A and this is B. All right. All right. No issues with that. It's a very simple idea, right? So dimension of A is 3x3. Dimension of this is 3x1, right? So there are 3 rows and 1 column, right? All right, no issues there. Okay, I'm not doing any computation here. All right, let's go with this. So I can always do a square of this matrix, right? What if I want to do a square of this matrix? Okay, a proper matrix square. Okay, so if I just say A star star 2, see what I'm getting? I'm getting element wise square. So 1 is being squared up, 2 is being squared up, 5 is being squared up, then this 3 is being squared up, individual square. Maybe I don't want that. I want to treat this as a proper matrix, right? In that case, I might want to convert this to a matrix. So for that, I might want to call this a matrix instead. Now, if I do that, then it becomes a matrix. It's no longer an array, it's a matrix. So if you want to see this, say if I say type A, it is no longer an array, but it's a NumPy matrix. Now it is going to be now treated as a matrix. So if I say a star star 2, a matrix square is going to be done. So now this is not doing individual element wise square. It is now treating this as a matrix, and accordingly it is doing a matrix multiplication. Okay, it is now doing a matrix multiplication. So by default, NumPy arrays, if you are doing something on a NumPy array, then it will do element wise operation, and by default, if you are doing some computation on NumPy matrix, it will treat those NumPy matrices as proper mathematical matrices, right? Not just simple arrays, like just like that. So that's an A square. Okay. So of course this discussion is kind of futile, not needed here. You can just skip this discussion here. Okay. This discussion is again not needed. 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 All right. Okay. So I just said you can do a matrix manipulation like that. So instead of doing this, let's look at this. Okay, fine. Let's look at this. Okay. So imagine this is a system of linear equations. This is a system of linear equations where you have 3 equations and 3 variables, 3 linear equations and 3 variables, of course. So the equation looks like this: x plus 2y plus 5z equal to 20. Then 3x minus 2y equal to minus 1. And then 7x plus 2y minus z equal to 8. If you have things like that, okay, and maybe you want to calculate the value of x, y, and z, right? So you know how to do that using matrix inversion, right? Right? So this is like in the form of ax equal to b. The answer would be a inverse multiplied by b, right? So the solution x, y, z would be like simple ax multiplied by b, the solution. So for example, the x, the solution basically, right? So it's going to be inverse. So how do you write an inverse? So since A is a matrix, you can raise it to a power of -1, and that will result into an inverse of the matrix. So that's an A inverse, right? And you can multiply that with B. That will be a matrix multiplication. And if I do this computation, and of course if I print x after this, that's the solution. So I came up with the values so that x has a value of 1, y has a value of 2, and 3 has a value of z has a value of 3. So I just solved a set of linear equations where this is matrix A and this is matrix B, right? So this has been done this way because I am treating A as a matrix, not as an array. If I treated this as an array, then it would just do the reciprocal of individual elements like that. Okay. One more thing, you can even do more complicated things like this. So this is A, right? That's just a matrix, right? Okay. You can raise this matrix to any power. What if I want to raise it to a power of 50? What if I want to do that? I can do that. Okay, I can do that. What if I want to raise our matrix to a fraction? So for example, what if I want to take the square root of this? Okay, it said, okay, here I cannot do that somehow. Okay, probably I needed to create a... Okay, fine. Okay, it does not allow me to do that for the moment, but yeah, just say I want to do this, that's fine. If I want to put a -1, okay, that's an inverse, matrix inverse. So if I take this, so this is, I'm saying A inverse. So this is A inverse, right? So, and if I multiply A with A inverse, what do you expect to get? Of course, this is A inverse. Let's print it. And if I multiply this with A, I'm supposed to get a identity matrix, right? So this is identity matrix of order 3. So the column element, so the diagonal elements are 1 1 1, just like that. Okay, so simple algebra, right? So forget those things. Again, I'm not going to talk about all these things, because whenever I need those things, I'm going to talk about this. Again, of course, within linear algebra, we have a function called determinant. You can calculate the determinant like that. Okay. 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 Important point. Same. Alright. Now, let's create a random array. So random array containing 100 elements, right? Now let's do a little bit of statistics here. So random array containing 100 elements, right? Let's do a little bit of statistics. Okay. So of course, what is the shape of the data? 100, right? What is the mean? The mean is around 5.5 something. Now, of course, if you have studied probability and statistics, you know, if I'm drawing drawing numbers from uniform distribution between 0 and 1, then the mean of the distribution is 0.5. So this is kind of matching with whatever data I have. Okay, and again, I can calculate the standard deviation. I can calculate the variance and everything. So this is the standard deviation. This is the variance. Okay, I can calculate what was the minimum in the array. So this was the minimum value in the array. This was the maximum value in the array. Okay, right? And also there are a few helper functions. So if I have an array, okay, say for example, this is an array I have, I can calculate the sum of the entire array in a single go without just, instead of creating a for loop and incrementing a certain variable named sum like that, I can, at a single step, I can calculate the whole entire sum of the array. Similarly, I can calculate the entire product of the array. Okay, I can do a cumulative sum. Cumulative sum means sum up to that point. Okay, similarly, I can do a cumulative product up to that point. Okay, so again, in NumPy we have trace of a matrix. Which is trace? Trace is the sum of eigenvalues, which is also the sum of the principal diagonal elements. Again, I'm skipping over these things because these are sort of less important. All right. So now these are kind of more important for our purpose, whatever we are doing. Right? In NumPy, we can create something called a polynomial object as well. So instead of just array objects, we also have some these are all fundamental objects. In NumPy, we have array objects, but also in NumPy, we have polynomial objects. So I can create a polynomial with coefficient 1, 2, and 3 like that. So if I want a polynomial like this, where the coefficient is 1 here, 2 here, and 3 here. Okay, so like that. So now we have a polynomial, which is this one. Now, why am I saying these kind of things are important for us? Because for our control system engineering, our transfer functions are polynomials. All right. If I want to evaluate the polynomial at a point, I can just pass in the point, okay, and it will be evaluated. So if x is 0.5, then this polynomial is this. Right. So what are the roots of the polynomial? Then this is an attribute. If I say p dot r, then it gives me the roots of the polynomial. So of course, the numerator polynomial and the denominator polynomial, we have a transfer function. So then that will have a numerator polynomial and a denominator polynomial. So I can, using this method, I can actually calculate the roots of the numerator and the denominator. The roots of the numerator are known as the zeros of the transfer function, and roots of the denominator is known as the poles for the transfer function. I can actually very easily see those, and these are the coefficients, right? Doesn't matter. And I can also see the order. Okay, so I created a second order polynomial. So I can, by that way, I can actually look at the order of the denominator, and subsequently I can say, okay, I have a maybe second order transfer function like that, right? Again, the same thing. Okay, polynomials can be added, multiplied, subtracted like that. Okay, just like transfer functions can. So if I multiply two polynomials, I get another polynomial out of it. Okay, if I can raise a polynomial to a power, okay, add something with it, and divide a polynomial with another polynomial. Okay, So I can do all of these things because, yeah, just like that. Okay, so it doesn't matter. And I can also change the name of the variable in the polynomial. By default, name of the variable used in the polynomial is x, right? So now, of course, in our control system engineering, we have the name of the variable is s, right? So now we have this kind of a polynomial, right? So I can say my numerator polynomial is 1s square plus 2s plus 3. Maybe by my denominator is, say for example 5s cube plus 3s square plus 6s plus 10, right? So let me just print the numerator. So this is the numerator's polynomial, s square plus 2s plus 3. This is the denominator's polynomial, 5s cube plus 3s square plus 6s plus 10. Okay, and say I can say my transfer function g is just the ratio of the numerator's polynomial by the denominator's polynomial. So num divided by 10. And if I say print g, unfortunately it won't be printing it as a transfer function. For that we would have different way. But just I have to understand that this g, for all intents and purposes, is a transfer function, right? Which we actually are going to use, right? So it's a ratio of two polynomials, right? So at any point, if you want to calculate the poles, so you would say den dot r. So that is going to give you the roots of the denominator. So I would say something like print, and I would do a formatted string. Say I would say f, and the poles are at, and then I pass in this one. String, yeah. All right. So the poles are at these locations. So these are all complex poles, right? And then there is one real pole like that. So you can understand that we can actually very easily calculate many complicated things about our system. All right. What if I know the poles and zeros, and what if I want to extract the polynomial out of it? I can just pass in the location of the roots, and subsequently we can calculate those as well. We can multiply like that. All right. So with that said, we are going to end the discussion at this point, stating that someone is saying, how can we find the rank of a matrix? Okay, let me go back to the discussion where we were calculating a few things about a matrix, right? Let me show you how to calculate the rank. Okay, say okay, what was A? Fine. A is a square matrix. Fantastic. And this matrix is invertible, so it is supposed to be a rank 3 matrix, right? It is supposed to be a full rank matrix. So I can say np.linalg. So np.linearalgebra.rank. I think it's np.rank. Let me see. No. I can pass in the matrix. Okay, say np.rank on A. Okay, fine. What? All right. Okay. NP. Okay, fine. Rank is supposed to be. Hold on for a second. Okay, matrix rank, right? np linalg dot matrix underscore rank. Okay, and now I can pass in that. All right. So I can pass in matrix rank. Fine. I can pass in that. So that was our trace. So I can print the trace of the matrix, rank of the matrix. So from NumPy linear algebra, so from NumPy we are calling the linear algebra module, and from the linear algebra module we are actually calling the matrix rank function, and from that we are actually passing the matrix for which we want to calculate the rank. So the trace was -2, and not only just that, you can also calculate the eigenvalues and everything. So print np dot linalg dot eigenvalues and pass in a. So those are going to be the eigenvalues along with the eigenvectors. So these are the eigenvalues of the matrix, and these are the eigenvectors. This is one eigenvector, this is one eigenvector, and this is another eigenvector. And these are quite heavily used in control system engineering, because these eigenvalues and eigenvectors of the matrix, system matrix, often actually determine the properties of a system, including the stability of the system, how the system behaves and everything. Okay, so, and we are going to learn how those things actually come into action. And these are very strongly somehow related to differential equations and Laplace transform. So in this course, we actually, in our theoretical course, we are going to actually combine Laplace transforms, differential equations, and linear algebra together. You're going to use all these tools as complements to each other, right? And of course, we are going to do everything programmatically as needed. All right. So any question that you might have? All right. So we had a pretty big discussion today, and you understand why I made this or made all these things before going into the class. Otherwise, we wouldn't even be able to end this in 2 hours, right? In any case, if you want to learn more about NumPy, you can always visit this. Hold on. You can always visit this. You can say NumPy documentation. Oh, what did I say? Okay, you can go to numpy.org. Okay, and go to the documentation. Okay, and of course there are quite a few tutorials and everything. As beginners, I would ask you to go to the beginner level tutorials, and if you're already an expert and you want to see what kind of functions and things are there in NumPy, so you can go to the NumPy API reference. You can see everything that NumPy can actually do. Okay, there are plenty of things that NumPy can actually do. In any case, that will be the end of today's discussion. Feel free to ask any question that you might have at this point, or we are going to end our discussion. And if you have any query, feel free to ask. Alright, so I have created a Google Classroom for you. Just please register there, make sure to register there. Your assignments will be provided there. So we are going to have 2 more classes on fundamentals of Python and as such, and after that we rather 3 more classes on fundamentals of Python, and then we're going to jump to doing control system engineering using Python. All right, if you don't have any more queries, we are going to end our discussion here. And again, if you have installed Anaconda distribution, you have this entire thing. You would have this entire thing installed already. And if you are doing it on Google Colab, then also the same thing. All right. So thank you very much. So this will be the end of our discussion. Thank you very much.